In this video, we will be learning about synthetic division. We will talk about synthetic division, how it relates to long division. We will talk about the remainder theorem and also find potential zeros of polynomial functions. Okay, let's first of all talk about the division algorithm. Okay, let's let f of x and g of x be polynomials. All right, where g of x is lesser degree than f of x, and g of x has a degree 1 or more. So basically, we have here by the division algorithm that we can factor f of x into a product of g of x times q of x plus r of x. Okay, so g of x is our divisor, q of x is our quotient, and r of x is our remainder. Okay, synthetic division is going to provide a shortcut for division to get polynomials in factored form. And it works when you are dividing by a binomial of the form x minus k. So x minus some constant k. Now let's take a look at an example where we compare side-by-side synthetic versus long division. So first of all, let's long divide. So when we long divide, what we do is we look at our leading terms, and then we multiply by what the quantity that's going to eliminate that first term here. So we have 3x squared. When we multiply 3x squared, distribute there, we get 3x cubed minus 12x squared. When we then subtract, okay, subtracting, we change the sign on every term of that second polynomial, and then we add vertically. Notice how those first terms zero out, and we're left with just the quadratic terms, 12 minus 2, which will give us 10x squared. All right, and then the process starts over again. So here we have our leading terms are x and 10x squared. All right, we seek to multiply the x by a quantity that will eliminate the quadratic. So I'm going to bring down this 0x first of all, and then multiply through by 10x. When I multiply through by 10x, right, that's going to eliminate that quadratic term. So I have distributing 10x squared minus 40x. Subtracting, I change the sign on every term of that second polynomial. Notice the quadratic terms subtract out, and I'm left with 40x. Now I bring down that negative 150, and the process starts over again. So now my leading terms are, see, we have x, oops, get that a little, we have x, all right, and then we have 40x, all right, so we want to multiply here by 40, because when we distribute across, that will give us the 40x that we're wanting to eliminate, and then we have minus 160. Subtracting changes the sign on every term of that second polynomial. The linear term subtracts out, and I'm left with 160 minus 150, which is a remainder of 10. So I can write the remainder all over the divisor, and that is my final answer. Now what we want to do is look at a shortcut. Now I can use synthetic division here because the divisor is of the form x minus k. All right? And so what we do here is we put our value for k out to the side, and then we write in the top row the coefficients of our terms here, which we have 3, negative 2, 0, and negative 150. Okay, and then by synthetic division, the steps in the process are to bring down the first term. So we bring down that 3, and then we begin a series of multiplying and adding. So I'm going to multiply 4 times 3, that'll give me 12. So I record it right here. Add vertically to get 10. Repeat, 10 times 4, is 40. I record it and I add. And then I do this again. I multiply and then I record and then I add. We set our quotient here apart from our remainder by putting double bars right there. So this, you'll notice, corresponds to what we got when we performed our long division. So we're getting the same answer, but we're getting it in a much more efficient way. So that's what synthetic division allows us to do. Okay, a special case of the division algorithm occurs when we are using synthetic division. We are able to factor f of x into a product of x minus k times q of x plus r. So looking back at the example we just did, if we want to factor f of x and write it as a product, then we would just simply say that f of x equals x minus 4 times 3x squared plus 10x plus 40 plus 10. Okay, so notice this is our g of x, right? Or our x minus k. This is our q of x, and this is our r. Okay. Now, let's talk about the remainder theorem. The remainder theorem tells us that if we divide a polynomial by x minus k, the remainder is equal to f of k. So let's take a look. So here we have a function f of x, and we're asked to find f of negative 3. So you could plug negative 3 in everywhere you see an x to answer that question, but we are going to use synthetic division to provide a shortcut, a more efficient way to do that. So k here is negative 3. So we're going to divide synthetically. Along the top row, we're going to write the coefficients. Notice I'm putting a 0 here for my cube term. And now I start my sequence of multiplying and adding once I bring down that negative 1. So we're going to multiply negative 3 times negative 1 to get 3, and then we're just going to add, multiply, add, multiply, add, right, and then here we go. Right, and so then our remainder would be negative 47. So f of negative 3 is negative 47. Okay, so the remainder is f of k. Okay, so f of negative 3 equals negative 47, again by the remainder theorem. Okay, and finally, we're going to talk about testing potential zeros, okay? A zero of a polynomial function f of x is a number k such that f of k is 0. So if we apply the remainder theorem and we get f of k to be 0, so like right here, if I get a 0 right here, then I know that I have located a 0 of my polynomial function, okay? Real number zeros are x-intercepts of the graph. So something to keep in mind that a 0 is also called an x-intercept. And this is going to help us greatly as we graph polynomial functions. Okay, in terms of steps, what we're going to do to find potential zeros is we're going to use synthetic division to find f of k. If the remainder is 0, then we know that f of k is 0, and we have found a 0 of f of x. If the remainder is not 0, then k is not a 0. So let's take a look. So applying what we just talked about to this problem, we are asked to decide whether the given number k is a 0. Remember, we can divide synthetically here, so we divide 1. We write down the coefficients of our polynomial along the top row, and now we divide synthetically. So we're going to bring down our first term, and then we begin our sequence of multiplying and adding. notice here we get a remainder of 0. When you get a remainder of 0, then you have found a 0. So if we are asked to decide whether the given number k is a 0, our answer is yes, k equals 1 is a 0, right? And that is by the remainder theorem here that yields a 0 for remainder. Okay, let's do the same thing here with k is negative 1. So same process. We are going to now begin by bringing our 1 down. Then we're going to multiply and add as we go. You'll notice here that for remainder, we do not get 0, right? So for remainder, we get 6, right? And since that is not 0, then we do not have k equals negative 1 to be a 0. So it's not 0. So k equals negative 1 is not a 0.